So just to recapitulate from the last time, what we learned is that we have peer-to-peer networks on top of the IP layer. So this is typically what we talk about. They have the properties of it should be self-organizing. They are all equal, so they all have the same code and have the same duties, and they all act as servers and clients to each other. And it's very dynamic. So we have nodes going online, going offline. They are very diverse in their capabilities, and we also have the issue that all the resources that we want to use are at the user devices. So it's a little bit tricky to use, and today we will have a look at unstructured peer-to-peer overlays. We didn't last time specify about what kind of categories of peer-to-peer overlays we have, so we just had a definition. And today I want to introduce some new classification so that you get an overview about what types of peer-to-peer overlays we have, and then we dig into each of these types individually to see how they look like, what are their properties, and what can we do with them. So first of all, to keep in mind what is new with peer-to-peer networks. Why do we have typically peer-to-peer networks? Typically, they introduce the concept of data, addressable data, so that we can either find data, search for data, or look up data. So what do we have? We have the devices, and they all provide, on one side, storage space. On the other side, the users also want to provide some data and to offer the data. And these users now have different opportunities to find the data. So if we have a node or a network of million nodes, so this is the one problem, the scale. So we have potentially millions of nodes. How do we find the single node that has the single data item that you want? And the second part, dynamism. So if the nodes go online and offline, and they change what they offer, and they change what they want, so we cannot calculate it up front and use this information, so we have to calculate it on time. And we typically consider two major query types in peer-to-peer overlays. These are very important to memorize. So on one side we have the lookup. This is like a URL where you define the ID of the object that you want to have, and the overlay gives you the node which has that, which is responsible for this ID. So like the URL, and you get the corresponding serving node. The good side is, it's like with the URLs, every object is uniquely identifiable, and if you type in that URL, this ID, then it is that specific object that you are looking for. And the network either gives you the document, or it's not available. So this is the ideal state. So it guarantees the availability and that you get it. And you can optimize how to find this corresponding responsible node. On the drawback, somehow we have to know the ID, so we have to know the URL, and we don't have Google to look it up. And we need to maintain, so if in this network of 1 million nodes, we need to maintain the information where the node responsible for this ID is located. On the other side, we have something that's related to search. So where you define a set of keywords or metadata or any quite freely definable definition of what you want. And what you want as a return from the overlay is the contact addresses of the peers which have matching results. So if you're looking for some music from some specific artist, or if you are looking for a Word document which you edited, then you want to get the list of these nodes which have corresponding matching files. And on the good side, so you don't need to know what you want, or you don't need to know the result for the request, but you also don't get always what. So the requests are not reproducible. So sometimes you get different results. So ideally, you would like to have all of the results, and in order to get all of the results, in the worst case, we have to search all of the nodes. So we have to have track of what all of the nodes have, and to make this efficient, that's quite difficult. So from the next 2-3 lectures, we'll focus on the right side, so on the search approach and how this can be solved. And typically for this, unstructured peer-to-peer networks are introduced. Because if you search for the data, then the name of the data is not so important. It's more important what kind of metadata they have, what kind of keywords they have. So they don't have a specific identifier. And we don't know where the object might be, so it might be everywhere. So we don't have any structured information about its location. So unstructured peer-to-peer overlays typically solve the search problem. On the other side, we have structured peer-to-peer networks that we will look at in 4 or 5 lectures. And there, both the peers and the objects have IDs. These are typically very large numbers, so from 0 to 2 to the power of 160. So you have 160 bits. And what you want to find there, and what the structured peer-to-peer overlay gives us, is to find the peer which is responsible for specific object ID. Because we have, of course, not the whole ID space filled with peers. That this is too many nodes, so there are more atoms in the world than to encode with 160 bits, so 320 bits. But so the objects are in between the peers somewhere, and there we define responsibilities for these peers for some objects, and we want to find the peer which is responsible for that specific object that you are looking for. And this can be made more efficient, but again, there you only find that object that you are looking for, and this is the lookup. Okay, so talking about different categories of peer-to-peer overlays, I also want to introduce 2 other kind of classifications, and the one describes on how much centralized items are used. So typically we were saying that in peer-to-peer networks, all of the nodes have the same roles. Yes, but from historical point of view, we also had centralized peer-to-peer networks where we had servers helping out to find the nodes which want to communicate with each other. From historical point of view, that's existing, but not anymore used so much. Then we have the type of peer-to-peer overlays where all of the nodes have really the same duties, so there are no different roles, all of them have the same code, and they do the exactly same protocols. In contrast to this, we have the heterogeneous peers, where the important part is they have different roles. So we might have 2 or 3 or 4 different kind of roles for the peers. Every peer can select its specific role, and in combination of these roles, the networks are performing. So for example, some of the overlays that we will have a look at use so-called super peers. It's a little bit I'm not sure whether well visible, but the super peers create an own network by themselves, and the normal peers are connected to the super peers, so we have different roles. But we will have a look what this means in detail, so just to know the terminology. Also what we have is our flat overlays. So most of the overlays that we look at are flat. So we have only one single routing protocol, and all of the users use this single routing protocol. On the other side, we can also have hierarchical overlays. So this is some extreme example, which is typically not used because it's very complex, but to know the terminology. So hierarchical peer-to-peer overlays combine different routing mechanisms into one big overlay. So for example, the routing in the blue overlay is among these blue dots, and one blue dot is a red overlay network, and one red node in this overlay is again a different overlay. So if you have typically this kind of routing in the internet, for example, border gateway routing, where you have for a specific network type, for example, the local area network, one kind of routing, and then you have exit points to the higher level routing. And this higher level routing could also have some exit point to some even higher layer routing. So we can have these overlays stacked over each other. Typically, this is not too frequently used because it's quite complex, but we should also know this terminology about flat and hierarchical overlays. Okay, we will shortly have a look at what kind of unstructured overlays we have. I just want to say how to measure. So when is a peer-to-peer overlay good? So for the structured overlays, what is the most important? That you find the object if it's there. So if you don't find it, then it missed its goal. So what we want to have is to find it. This should be the most important. And in order so the probability of success And for the probability of success in unstructured peer-to-peer overlays, that's the point that we find all matching documents that we want to see, so that matches to our request. And typically what is measured there is how expensive is this process, so how many nodes are visited, how many messages do I have to send for my request to be answered, how many nodes are visited during my request. So if I send out a lookup request for one specific object item, how many nodes are involved to resolve this lookup. Or if I search for one specific keyword, how many nodes are contacted and have to react. And this is a measure for the costs it produces. Also, we can have a look at the costs from the point of view whether the load is balanced. So do we have some peaks, one node which is very overloaded with traffic? Do we have some congestion points? So this is typically some measure. So the costs, and on the other side, we typically try to measure the probability of success, so to get all of the requests successfully resolved. So completeness, so are all the results returned? This is one measure. The other point is, are all of the returned entries valid? So do you know when this might be not the case? So we get a result, but it's not valid. Do you have any idea? So when is a result not valid? So typically, if you update your data, so we do not want to look only at read only, no, at write once and read many systems, so where you only upload your data once and that's it, and it never changes. But on the long term, and if you want to use peer-to-peer overlays for more various applications, then you also want to be able to change the content of the data. And then you want to make sure that the data that is returned to the users that are interested in it are always up to date and not some old data that was not captured by the update. And it's always also important how long does it take to resolve the query. There are some, for different applications, some thresholds when it is unacceptable for the user to wait, when he doesn't want to wait, and then he quits the operation, so we want to really know how long does it take. Okay, this is about how to measure it, and in the next we will go into detail about the unstructured peer-to-peer overlays, starting with simple centralized overlay just from a historical point of view, and then homogeneous networks, and then heterogeneous networks. And once we cover those, so in 2-3 lectures, then we will go over to the structured peer-to-peer overlays. Okay, let's start with the centralized approach. This was basically the first one that came up, and this was the big invention of Napster at that time, in 1999. So what and how Napster revolutionized the content and distribution of files. So previously, you wanted to have a file, you had to upload it, or somebody uploaded it to a server, and then you could download it from the server. This was okay, but it didn't scale. So of course, you need, the more and more users are participating, the more powerful the server has to be, and the more parallel queries it should be able to serve. But what centralized peer-to-peer networks at that time introduced is that the server does not contain the file, it just contains the information, which file it is. So somehow, with all these keywords, like at that time ID3 tags in MP3 files, or file names, and it contained the information which nodes do have this file. So it had the information about what and where, and it could be asked to tell us, give us the contact information of a node who has this data. So every time a node came online and he wanted to share some file, he contacted the central server, told the central server what kind of files he have, but he didn't upload them, so this metadata is quite small. And later on, if you wanted to have a file, then the central server was again contacted. We will see, so there will be an example how it's used, but we also see in this point that the central server is a bottleneck. So if the central server is gone, then we don't know where the files are and they cannot communicate. And this was also the point why Napster could be shut off easily at that time. So what is the approach? So here we have some points. Yeah, so this should be number 5. One moment. Just, you know what I mean. Okay, so first of all, just ignore the lines. I will try to correct them for the next time. But the first step is node A. Node A is down here. He stores first the file that he wants to offer. He stores the information about the file at server D. And server D knows now, okay, A has this file and all the specifications about the file. Then the next step is that node B contacts the server. I would like to have a file with this and this specifications. It should be a song by, I don't know, any artist. Justin Bieber, I don't know. And then the server tells, okay, I have information about this file. I have a few matches. At least node A is storing the file and he's responding back. So as a fourth step, what Napster did, and which is somehow optional, but Napster did, so node B checked out of all of the providers the bandwidth quality. So he sent some ping message, it was returned with a pong, and from that the delay could be calculated somehow. We could the node also could see what bandwidth there's available. And once you know somehow rough estimation which nodes are good and closely to you, then out of this list of potential providers, node B selected the best one and asked for transmission to send the data to node B. This is a simple approach. And from looking at the advantages, it works. It's simple to set up. So for the nodes, the code part is very easy. For the server, the coding part is very easy, and it's working. Do you see some disadvantages? One was already named. Yes, you probably see some, yes. Yes, so that was one point exactly. And also, so the scalability was not, so the security point of view was given that that's a single point of failure or attack. So you could both switch it off, or you could monitor the peers, what they are sharing, and use it for your purpose to sue the users. On the other side, even if it's not shut down, it's not scalable. So you have to add more and more server power in order to allow it to operate with high number of users. And especially this increasing implementation and maintenance costs are non-linear. So you have to add more and more powerful devices, and it's getting more and more expensive. But if you have a very small and not really risky application, that's still something to consider to implement. Okay, just to summarize, so this was basically the functionality of Napster, and this was also the first so-called peer-to-peer network that came up with that term, and it was really getting very popular with a few millions of users, but they were forced after 2 years, 2001, to implement some filters. So you couldn't look for Britney Spears, but you could look for Britney sparse or something. They could modify the letters a bit, so they had very simple filters. But also that was not allowed, so they had to close. There were some open other alternatives, but now this kind of concept doesn't work anymore because both the users noticed that it's not working out. They cannot share data as they wish, and they are monitored too easily. And also the copyright owners didn't allow any kind of operation in this field. Okay, so let's see how the unstructured P2P overlays, the pure overlays where we don't have special servers, how they operate. And before we go into that, I want to discuss with you some search properties. So how can we search? So just assume we have 1 million nodes, and all of the peers are equal. So think about some, so there will be a question here. So just keep in mind, so the question will be identify various search mechanisms for random networks. So what is a random network? So we have every node is equal, they have all the same code, and somehow they have to have a search mechanism. And one of the nodes in this, or a few of these nodes in the network have the file that you want to have. It's a very prominent Britney Spears song, I don't know. And all of the nodes, of course, just have a local view. They are just connected to some of their neighbors. What's also characteristic is that organic growing. So if a new node enters the network, there's no specific place where he joins, so where he connects to the network. So it's typically randomly connecting to any one of these nodes. So the network grows in any direction. Any node can be a connecting point. And what we want to have is to have a search mechanism that's self-organizing, that is finding the data. So what tasks are solved? So first of all, to connect to the network. So there are some joining strategies. Typically, what is done is that you need to know at least one peer in the network, and then you connect to it. And over that node, you get to know other nodes, and you can connect to those. And then you build more and more links, and you are part of the network. So we have the connection to one node, and then we have some advertisements which connect you to the rest. Then we have some search mechanisms that I will ask you now on the next slide what you could do. And after using the search mechanisms, let's say you search for the music file that you were interested in, and you get a list of 10 nodes who have that fit to have music files which are fitting. They are presented to you. You can select which you want. Probably for the same file, also different sources appear. And then you establish direct connections to those nodes which have those files, and you download the file. Okay, so preparing the question. So what kind of search mechanisms for these random networks can you think of? Just as a hint, so what we also can think about is how we insert new files. So how do we announce them? How do we search for the file? And probably some statements about is it costly or how much of the results do we get? Mm-hmm.
The simplest way, but the most inefficient also would be flooding. I flooded to my neighbors and they flooded to their neighbors until everyone in that network has their information.
Okay, that's good. So in that case, the inserting of the file would mean we just leave it at our device, and if a flood comes by, then we just respond. Okay. How would you limit the spread of the flood so that it doesn't go on and doesn't end?
You can have some checks on like a hash or something, and node already knows that hash.
Okay, this is one option. So this is one option. That's good. So what else can we do to make it probably not so expensive at the cost of also not having so good results? Yes, that's also an option, that you that you introduce something like a time to live, and only in this region you search. Okay. But probably you also want to leave that region. Probably it's just related. So if we would think about some random network, and somehow it's also geographically aware, so the German nodes are connected to German nodes, and it's more, then we wouldn't leave Germany, but we are interested in high quality Japan music, I don't know. So how could we overcome this limitation in the hop count, but still not reach too many nodes? There we will also see an example, but probably another question, could we do something to improve finding the data by inserting the new file a little bit different? So what would you typically do if you have something to announce, and you want to be found, or you want to serve the community? What do you do? So you want to sell something on eBay? What do you do? Do you keep it for yourself, this information? Or let's say you don't have eBay, but you want to sell something, and Do you wait for your friends to ask you what are you selling? Or no, typically sometimes you also announce it and give some advertisements around, and then you hope that somebody will find the advertisement, not directly you, but the advertisement will be found. So we will see what kind of examples we have. So first of all, like you said, the flooding, this is one of the most simplest and prominent examples. And that assumes that we have this network of millions of nodes, and we don't know, don't have any information about where the data that you are looking for might be. So we don't spread any information about it. The content that is provided by the users are just stored at their devices, and they are waiting for the flood. What is a flood? This is a breadth first search, so Breitensuche. So you start from one point, and you send it to all of your neighbors. So this is let's say the initiating node down here to the right, and he sends a query to his one neighbor, but he sends it to all of his neighbors, and this neighbor sends it also to all of his neighbors except the one he received it from, of course, because the initial node already had it. What we can do to limit the distance, one option that you said is to introduce some checksum, so to recognize that this query was already observed. The problem might be that you have to have a very big cache for the checksums that might introduce some new, so how long do you keep the checksums? That would be a question. So just to say it's also used, but it's also added with a time to live, so every query has a limited number of hops it can go. So let's say 7 or 4, and after the 4th hop or the 7th hop, it's not anymore forwarded. In order to do this, we have a little information in the packet that is sent around in the query telling how many hops it can go. And if it's once it's 0, then it's not anymore forwarded. Okay, this, like you said, so we could use some checksum. This is the so-called message identifiers, which are making sure that, let's say, over some circle, the query comes back to the node which already sent it out, so he doesn't have to resend it because the information is not new. And this is true. So this approach provides us with very high completeness. So we, in the worst case or in the best case, you reach all of the nodes. You can ask all of the nodes, but it's also very expensive because every single query reaches all of the nodes, and this is quite expensive. It's a nice animation. Okay, so it was just sending around the message. As you see, there are around 43 messages sent, and we find a path which is 5 hops away. So this was the 1, 2, 3, 4, 1. This is the first hop. 2, 3, 4, 5. So I should have started numbering with 0. And this is we've also find the shortest path to the peer, but it doesn't matter because after we find the corresponding peer with the file that you want to have, we establish a direct connection that we can do and transfer the file. Another point that we can do, so besides the flooding, is to try to limit the cost for to make a trade-off between the cost to send messages, to send less messages, yes. On the other hand, to take the risk that we miss some files, miss some nodes which have potential files. We will also come to that, but one point how it can be optimized is the expanding ring. But before I explain the expanding ring, I would like to introduce you to the Zipf distribution, because if we talk about typically files that people share and data and documents and everything what is related to people, typically the distribution about the popularity is not equal. So you have popular files and you have less popular files. And there has been some observations which, based on what people look for, what they buy and so on, and there's a model which allows to mathematically describe this popularity, and it's the Zipf distribution. So this is something also peer-to-peer related you should memorize very well. And that describes in a fixed set, so let's say the set has 1000 elements, it defines for every of these elements the probability that it is searched. So in sum, all of the probabilities are 1, of course, and for each individual element it tells you what is the probability that the next element which is searched is the one which is the 623rd most frequent one. And this is it is defined like this. So it's not too complicated, I must say. So what you just have to understand it. So in the lower part of this formula, there you see, or let's start here at the top. So first, the K, that's the rank that we have. Yes. So K is the number 623. So we want to calculate for the object with the popularity number 623, what is the probability that it is selected next? And we have only these 3 parameters. K is that's the rank. S is the gradient by which this popularity is skewed. So if you would take something around 1, then it would be very equal, and if you take a lower number, then it gets more different between the most popular and the second most popular. So so the differences are bigger, the smaller S is. So and this upper part tells you just take the rank and take it to the power of this factor S, and it gives you a number. And then you put it in context to all of the other such calculated values for all of the other ranks. So because so if we introduce for this small n all other rank numbers, so the rank is the 623, and we would calculate from 1 to 1000, then we get here the probability if we sum it up for the first ranked object and for the second and so on. So we calculate all of these numbers, and this is the relation of this specific object in the relation to all of the object popularities. And this gives a number between 0 and 1. And this is the probability that this node, this object is selected next. So very roughly said, it's that you take the number, the 1 divided by the rank, and you put it to the power of this factor. And if we have a look at some rough graph, how it looks like, so the most popular one, let's say, has a popularity of 1%. The second one is multiplied with the 0.6, and the third one is again multiplied by 0.6, and so on. And we decrease logarithmically the probability of the objects. And now I introduced all this popularity thinking. So why is this useful to optimize our search? Do you have an idea? Yes?
Just take the most popular files that have the highest probability and spread those further to other nodes.
Yes. That's true. So if we would know which is the most popular file, then we could spread it along. But we don't know. So we cannot, if we provide the file, we don't know how others like it. So there's also another point that somehow is very natural, but should be mentioned. Of course, the popularity of files that are offered are the same as the popularity of files that are searched for. So if you have something very popular to offer, then many people will search for it. Any idea how we can use it? No? Okay. So one approach could be if most of the queries are for very popular files, then the hop count doesn't have to be too big for them. So what you can do is to start with a small time to live, with a small hop count, and the chances are high that the user looks for a document which is very popular because they are popular. So let's say 50% of all queries will be solved with a small time to live, with a small hop count. And furthermore, 40% will be solvable with an increased time to live. and only very few queries will need a big time to live and a big search radius. So this concept is called expanding ring. So you start with a small time to live, you search only in a small environment because most commonly you are looking for something popular which is also provided in your neighborhood in short distance. And if it's not there, but 50% let's say of the cases are covered with it, if it's not there, then another 30-40% can be covered if you increase it from 3 to 5, let's say. And only very few queries are left which have a very big time to live at the end. The drawback is, of course, once you did the once you search in a radius of 3 nodes around you and you didn't find it, you have to extend it to 5, and then you search the nodes that you already have searched. So you double the costs for those, but still, considering the overall gain that most of the queries will be solved in the first few hops, it pays off. So we have, in average, an improved cost. So we have less costs because most of the queries are solved only in a small surrounding, and we don't reach too far. We don't generate unnecessary messages. The message overhead is still high, but we are still able to find all documents if we increase the time to live more and more. And in average, the costs are a little bit smaller. Okay, what you also can do is to have random walks. So now we leave the trail of searching all nodes. We only want to search a few, or somehow a number of nodes that we can have an impact on. So let's say we want to reach 2,000 nodes. It doesn't matter how large the network is, and then we want to try to find in these 2,000 nodes the files that we are looking for. So how can we do this? This can be done by random walks. What is a random walk? So here the trade-off is between not searching all nodes, having less costs, but still having a high chance to find the data. So what is a random walk? A random walk is if you send your query not to all of your neighbors, but only to a specific number of neighbors, which is typically a factor like k. So we will use this factor later on. That means if you select k equals 2, or in this, let's say k equals 2, then you only send it out to 2 neighbors. There's multiple random walks. What does it say? There's also different factor how many multiple random walks the initial node sends out. So just assume the factors are the same for the first case. And also here we have a time to live. So it's basically like the flooding, just you limit the number of nodes, your neighbors you send your query to. So let's see how this works. Let's say we have a random walk with n equals 2. So every node sends out his message to 2 other nodes, although they have more neighbors. And if the animation is correct, then every node sends really only 2 messages out. It goes along and also finds the one single node which has the data. So the nice thing is with the time to live and with this parameter n or k, you can control how many nodes are reached. It's really the hop count, 2 to the power of the hop count. So it's simply calculatable. On one side, it takes most typically longer to find the path to the corresponding node, and also you limit the number of peers that are searched, but we have a high chance that we still find the data, and we have used for that a calculatable and a controllable number of messages, and we don't explode exponentially like in the flooding. Okay. Are there some questions for these 2 concepts or 3 concepts up to now? Some unclarities? Because we will have an exercise about it to really understand more in deep how much costs are created by these approaches. Okay, another point how how unstructured overlays can work is through rendezvous. And here we do not leave the data item only at our node, but we want to announce it. So we make both an announcement in a specific region, and the nodes in that specific region store the information that we have the file. It's called a data bubble or an announcement bubble. And also, if you make a query, you also send out in this limited environment your query. And if you, it's called a query bubble. And if the query bubble meets a data bubble, so there are some nodes which are in both announcing and query messages, then they will respond that we have the file and can be downloaded by us. So this is the idea. So the uploader replicates the announcement about the data randomly, and that increases the chance that it can be found. So what do we gain? So let's make a test, so an example. So it's a very related question. So just think about something else, about birthdays. And how many students do we need in this lecture to be in order to have 2 students with the same birthday, with a probability higher than 50%? Just think about it for 2, 3 minutes, 4 minutes, probably. And then we can see what's the outcome. And it's because the rendezvous point is very much related to it. Just think about it, 3 minutes, talk to your neighbors. So do you have any idea? Yes, that's it. And why is that 23? Do you know?
I think we just made a more distribution, just plot it out on a graph and just compare
Okay, that's the approach. No. So how many possible birthdays do we have? So 365, let's say. And we can calculate the probability that the first, so let's say we have an empty room and a new student comes in. What's the probability that he has a birthday like someone before? So, or that he has a unique birthday, let's say it's 365 over 365. Then the next student comes in. So we have already 2 students, and the probability that he has a birthday different than the ones before is 364 over 365. So that means this is, let's say, the probability to have this event is P1. The probability to have the event is P2. So the probability for the event P1 and P2 is P1 times P2. Okay. Then the same with the third student coming in. Then he has only 2 days less left. So 363 over 365. This is P3. And you see, so if we have all 3 events together, that means that all of the students have different birthdays to each other. Then it's also the product of all PIs before. And if we continue on, you see this is starting at 1. And this is getting lower and lower. And here's a small table. So it's really the 22nd. No, if 22nd students are already in the room when somebody comes in, then there are only 365 minus 22. So for the 22nd student, I have to write it, not sure. So for the 23rd student, there are already 22 in the room, and the probability that we have a common, that you have a new birthday is 343 over 365, 356. So this is this probability, 0.939726. And if we, so this one, and if we multiply all of the previous probabilities up, then it's on 0.5. Sorry. Ah, yes, okay, sorry, yes, you're right. Yeah. 265, yes, you're right. Okay. You know what I mean. So, so the point was that the probability that you do not reach someone with an announcement, so in this case, the days are the peers, and the birthdays are the matching nodes. And the probability that we do not meet a matching node decreases with every matching node that we have. And for example, if we would have 10,000 nodes, how many nodes would we have to have a match? It's around 116. And if you scale this up, then it's roughly the square root of the number. So it's a little bit off. So for 365, I think it's 18. So we have 5 more. And in this case, it would be 100. It's a little bit, but it's roughly the square root, yes?
That's only assuming only one node has the file. Multiple nodes have the files, the probability would increase, right?
Yes. So if more nodes would have the file and they would also make an announcement, the probability would increase. So that's true. So here, it's only that even one single node has the file, the probability, so that we only have to search a square root of the number of nodes in the network. How many nodes did we have to search with the flooding to find that single file? Do you know? Yes? Yes, O of n. And now we have O of square root of n. And this is quite good. On the opposite, so this is for the search. And for the announcing, we had O of 1. And here we have also for the announcing O of square root of n. So for this rendezvous. So we made it more expensive for announcing, but the searches are much easier. And taking into consideration that typically people search more than they offer new files, it's an improvement. And still it offers this search functionality, so you can define in your announcement bubble the keywords that you match and the file that it's matching to. And it's the same functionality, it's an unstructured P2P overlay. We don't have structured information about where the data is, so we don't use any IDs for the file. Okay. Ah yes, this is, I think, again, such a visualization how this network might look like. So here in the one on the right, the green node. So if it's printed, then it's light gray. So on the green node announces that it has the file, and this is the green dotted lines show where the bubble is spread, for example. And the requesting node, the violet node, is also creating its request bubble, and there are two nodes which have a rendezvous point, and they tell the searching nodes, yes, I know the information about where the file is located. And we will see if when we have a look at these are just the search concepts. There are specific overlays behind which are implementing it, and when we have a look at the specific overlay, then we will see how nicely you can really define how large your bubbles should be, because you know it should be around square root of n, and you can really tell it should be exactly, in our case, either 23 persons containing in the bubble, or 116 nodes containing in the data propagation bubble with 10,000 nodes. So it's really nicely doable. Okay, so these are some. So we got to know 4 search types. It was the flooding, it was the little modification, the expanding ring, the random walk, and now this rendezvous point. And next we will learn about the protocols which are implementing these concepts for unstructured peer-to-peer networks. And we start with Gnutella 0.4, as this is a very nice example about how the flooding can work. About the history, so Gnutella version 0.4 was announced just around the time when the problems with Napster occurred, and it was developed by Nullsoft. So some of you probably used Winamp. That's the same producer, and they were bought by AOL. And just around the date when they were bought, they announced the code. So somehow it was, some say, okay, AOL is announcing some file sharing application which motivates the people to buy high bandwidth network connections. So it might be some marketing product, some say it's not, but it's an option. And so if you read about Gnutella, there are 2 versions, 0.4 and 0.6. So now we look at 0.4. Later we will have a look at 0.6 later on. The difference is that in 0.4 the nodes are all homogeneous. They have the same roles, the same tasks. There are no differences. And later on they introduced differences, and we will see why they did it. Because 0.4 has some drawbacks. Okay, what's the main idea? The main search concept they use is flooding. So the nodes will be seen in more detail, but the nodes connect to each other randomly, so it's a random network, and the searches, the queries are flooded. And initially, they use the time to live by 7. And what they also do is that the node memorized some message ID. It's called globally unique ID, and do not forward them twice. And that's quite it. They only have 6 message types to operate, and we'll see how they are used. So first of all, they are sorted in 3 categories. So 2 message types are for connecting, to connect to the network and to announce yourself in the network, to be introduced to new nodes so that you can connect to. Because as it was said initially, typically you start your connection with connecting to one single node, but this is not good enough to create a network. So ideally you would like to be connected to 20 or 40 nodes. So how do you do it? You send a ping message which announces you. So I'm here, this is my contact address, and that's it. And you receive from the node that you sent it to a pong message saying, okay, I'm also here, and this is my contact address. But you will see what the node also does. He forwards your ping message to his neighbors. So his neighbors will also learn about you, and they will also answer you. So within the next round, the neighbors of your first neighbor will answer you. And in the third round, you can also ping them, and their neighbors will answer you. So with every ping that you send to your neighbors, you you extend your radius of knowing peers. Okay, this is for connecting. What we have for search is the query message. So you type in what you are interested in, and that's it. And a query hits, so then it's flooded. We'll see how it's flooded. And the response is a query hit, and it tells which files they are and how you can contact the nodes which have these files. And let's say, okay, now you know which are the the nodes that have the files that you want to have. Now you want to establish a connection to them, but so how do you do it? So for that they use the HTTP protocol. So that's what they suggest, so that you use this HTTP GET, so to enable the connection to those nodes and to download the files. But you might also have the problem that the nodes that have the files are behind the net or behind the firewall and cannot be contacted from outside. So what you have to do is to send him a push message about the path that you already have, to tell him, please contact me, because I can be contacted, I'm awaiting your contact, and push me the message. Okay, so how does this look like? So going through the steps. So first, the connecting. The aim is to join the network and to learn about new nodes and to connect to those nodes, so that you get more and more contacts until a state that you are happy with. So first, the new peer contacts any node in the network and sends him a ping message. And a node that was contacted answers with a pong message, which contains the information about him, how he can be contacted, but that's nothing new for you. But the more important point is that he also forwards it to his neighbors. And they reply also with a pong message to you. And they don't contact you directly, but they contact you over the node they received the message from. So you see, this is the path the pong messages take from the neighbors of your neighbor. Any idea why we have this like this? So why don't they connect directly to you? So what could happen if they try to send you a UDP packet? So what happens typically if you are sitting at home and your router receives a UDP packet from an unknown IP address? Yes? Yes. So it cannot relate where to forward it to. So typically you don't have such relaxed firewall rule that any packets coming to a specific port are forwarded to your device. So typically if you don't know this IP address, it will be true. But the connection to this initial neighbor already exists because you initiated it. So all incoming message over that node will be handed over. So it will pass through your firewall. So you receive the information about these new potential neighbors, and you could try to connect to them. Some will work, some will not work. But for those which work, you have now as new neighbors. And as a next step, you have probably not anymore one neighbor, but let's say 2 out of the 3 will work. So you have 2 new neighbors to send a ping message to. They will also reply with their neighbor ring. So they will send it to their neighbors. Their neighbors will send their pong messages, so you can extend step by step your connections and be better bound into the network. That's good. When searching, so let's say we are now in the network. How do we search for the files? So as I said, so we define the keywords that we are looking for. We define the time to live, and the time to live is used to limit the hop count of the message, of our query message. And there's some, for all nodes, known time to live. So it's pre-configured in the devices, so they are not in the messages. They list the hop count in the message. That's very similar, but you don't decrement the number, but you increment it until the nodes identify, okay, the hop count is still below the configured time to live, so I forward it. And if it's above the time to live that is in my configuration, then I will drop it. Okay. So they just forward it until the hop count is still valid and the query message was not received before, and that's it, to all neighbors. Once the node receive a query which they can relate to, they have some data for it, then they still continue with the flood, but what they also do is they create this query hit message and they list which of my files match this query, and they send it back, so both with their contact details and the files that are matching, so information about the files, they send it back to the querying node, also taking the path that the initial query was taking. And again, here we don't need to establish new links in this step to avoid the net problem or the firewall problem. So for the data transfer now, so now we get probably the information about 3 nodes that they have our data that we are interested in, and now we want to contact them. So again, here we try directly to contact them now. This is something new, so we establish actively the connection to them. So this HTTP GET is not part of Gnutella, they just recommend to use it, and let's say that this is what we use. And it might fail. So it might be that the nodes, again, cannot contact us. We cannot contact them because their firewall is dropping our request. So that's why they introduced this push message. So because you have the path to those nodes somehow, and the nodes on the way, so this middle node can memorize based on the query ID where it came from, where it sent the query to, and the query hit. And you can ask the intermediate nodes, so please send this push message to the node I received this query hit from, and tell him to connect to me. So he should establish the connection to me. The reason is, so you might be not behind the firewall and be connectable, and the push would work. And also you could configure your firewall in that way, or that for specific, I mean, you already know from whom you're expecting the connection, and you can use it to open the port for him. So this push message allows to contact the node that he should send you the data. It doesn't work if all nodes are behind firewalls, then we need other approaches, but it increases the chances that it will work out. Okay, what kind of drawbacks do we have? So one point that we have is, even with a hop count of 4 and with a normal number of contacts, we get already to know 8,000 nodes. And considering that in the Gnutella the hop count was 7, it would be interesting to calculate how many nodes are calculated, how many nodes are reached by this, and how much traffic do we generate with one query message. And because it would be interesting, I just jump to this slide, because I will jump back. So I will put online on the website this kind of exercise. So I was trying to put it into the slides, but it didn't work out because we are approaching the end of this lecture. So I would ask you to prepare until next week, Thursday, the answers for this exercise. So it asks you first about how Gnutella works. So if we have this kind of topology, who is sending to whom the messages, and what is the hop count, to just get some feeling. Then what would happen if you don't have state information, if you wouldn't use the message, globally unique identifiers. And then to calculate, it's doable, so to calculate, so how many nodes are reached by one query. So calculate the number of users, calculate the traffic that is done by a single query, and what's the total traffic considering all aspects. So this would be some tasks to look at for the next Thursday. Okay, jumping back. Like I was initially saying, so even with 4 with a hop count, with a time to live of 4, it's already quite difficult. And we will see, so surprise, surprise, that with a hop count of 7, it's even more difficult, and quite a lot of the bandwidth is used by these queries. So although it is fully decentralized, through the flooding of the messages, it's getting very slow. So most of the traffic is used either for the queries to many, many nodes, or for the ping and pong messages. Because as I also said, so we see that this is some measurement from, I think, 2002. And the most dominating factor was the query. The other dominating factor were the ping and pong. So if you contact your neighbors and they contact their neighbors and they answer to you, it's also generating 40% of the traffic. So most of the bandwidth that you have was really consumed by the queries and this connectivity messages. So it was very difficult to have bandwidth available for data transfer. And from a specific number of nodes, the more popular the network grew, the more of these kind of messages were used, and the less bandwidth was available for real data transfer until the network really then collapsed and no searches were anymore operatable, and it didn't work anymore. So what could be done to overcome these issues? So besides calculating how big the issue is really, so how many messages are really sent, so this is the part of the exercise, but what can be done to reduce this problem? So one option is to have another number of hops, so different time to live. Do you have other ideas what we could do? So if we have this kind of fully decentralized network, what can we do? Just ask your neighbor what they do. Probably they have a good answer. Yeah, we could use another search mechanism like we have had with Rendezvous, for example. We could also use do you have some idea how to combine the previous, so this centralized approach with this approach? So to reduce the drawbacks of both solutions. So the first drawback was of the centralized solution that it's a single point of failure, the nodes are overloaded, and here you have the point, so we had single point of failure, and here we have full decentralization, so no single point of failure, but it's too expensive. So what could we do, for example, to combine them? How would you combine those solutions? So okay, one option would be, so the nice thing about the server was that one node was maintaining the metadata information of, let's say, of many nodes, let's say 100 or 1000. Why don't we take many of these kind of serving nodes that contain the metadata information about what other nodes offer and connect them with this kind of Gnutella network? So then every of the single maintaining node could fail and the network will still operate, but the routing and the queries in this Gnutella overlay on top of the serving nodes is not so crowded. So the serving nodes will try to answer the first queries. If they can answer, then it's good, and if they cannot answer, then they will send it around in the Gnutella network. And these points, these ultra peers that we will have a look at, and also Gnutella 0.6 was using this idea, so that we that we introduce this kind of ultra peers or super peers, which manage the data available in various, let's say, 100 nodes, and they are connected. These ultra peers are connected in this Gnutella fashion, so that the load from the Gnutella network is reduced by the factor of 100, and still every node of every ultra peer is capable to serve 100 nodes. That's not too difficult. What also can be done is to optimize the ping and pong scheme, so that you introduce some more adaptive aspects. So if you have enough context, then you don't send ping and pong messages, or that you also introduce some probabilities when to react to pong or to ping messages, so that you try to reduce this connection of the nodes in a way that they don't spend so much traffic. We can also throw out the low bandwidth connection, so everything, all the nodes that are too weak to forward messages should be in a place where they don't have too much to do. So they should be at the edge of the Gnutella network or connected to an ultra peer. So they are anyway weak, they connect to the ultra peer, and if they have a few requests, that's okay for the ultra peer to handle. Also, what could be done is to reduce the file number. So once we introduce file hashes, then we don't need too many responses. So then we could also show, okay, we already have multiple sources for a specific file, and we don't have to forward this query further on. Yeah, and as I said, Gnutella 0.6 is using super peers, so they use this more powerful peers that are capable to serve, let's say, 100 nodes that are slow and weak, and they connect to each other in this Gnutella fashion. So we have this hierarchical solution. We have one Gnutella overlay, and every node in this Gnutella overlay is like a centralized peer-to-peer network maintaining the load of 100 nodes. What other problems they had, and sometimes still exist, is the concept of free riders. So I just want to name it here because you always have to keep it in mind. So if you have that kind of file sharing networks that live from the nodes forwarding the data and offering files, and what was found out that 70% of the Gnutella users share no files, so they don't participate in helping others, and also 90% don't answer to queries. So if we have this kind of very big community and very big network, then only few really participated in providing something, and all others were just misusing or using these services. So when we want to create a good overlay, then we have to also keep in mind to have incentives, so some motivation for the users to share their resources, so that they forward data, that they offer files, and there are different aspects how this can be made. So just keep it in mind that we also want to have a look at this. Okay, so this was the point about Gnutella. So we saw that we have this few message types, so 5, or let's say if we consider the HTTP GET also as one, then we have 6 message types. We are able to connect to one single node and to learn more about the network, to connect to those nodes, to more and more nodes. We have the search, the flooding approach, and we had the option to overcome the limitations of the firewall by the push message. So it was very simple. In small scale it was working fine, but as the network grew, more and more load was put on the nodes, and that's, as I said, I ask you to fill out this exercise until next week on Thursday, so when we meet, and it's about how Gnutella works and how many messages are created with one single request, and it's very interesting to see. So later on I will try to put in the exercises more into this lecture, but in this case it was a little bit tricky. Okay. So I'm just, okay. So we can have a look at the concept of one approach for rendezvous-based search. So we will start it and then continue next week on how this is working. So the rendezvous-based approach, as it was said, there the idea is that we have both an announcement bubble So we don't leave it just at our device, but we want to have an announcement of O of square n copies. So it doesn't have to be copies, it can also be just the information about where the data is to be found. So we need the announcement bubble and we need a query bubble, and the probability, if both are O of square root n, then the probability is higher than 50% that we have a match. And if we put a factor before this O of n, so let's say twice or 3 times O of square root n, then we can also reach 99% for a match. Okay, so how's the overlay named? So the overlay is termed Bubble Storm, because we have bubbles, and it was announced 2009. And there the assumption is that the nodes are in a random topology, so they don't have any structure, we don't know anything about how they are connected, everything is randomly. And that allows so this randomness is necessary to have this effect of picking the nodes correctly so that the bubbles work. So if you would have a line of nodes, then O square root of n doesn't work. So you really have this, it must be random. Then what also BubbleStorm introduces, because it wants to create these bubbles of specific size, it also introduces the topology measurement. So it wants to calculate how large the network is in order to know what square root of n is in order to make the bubbles that size. In this lecture, when we talk about BubbleStorm, we will not talk about how it measures it. There will be lecture number 10 or 11, which is about monitoring and measuring network sizes. But just assume that you know how large the network is. Okay, then if we know how large the network is, then they introduce a protocol which is introduced next. So this is the core, this is Bubblecast. And Bubblecast is an option that allows you to contact a specific number of nodes in the network. So if you say I want to reach 170 nodes and give them my announcement or my search information, then you exactly reach 117 nodes. So this is what Bubblecast can do. So this is very different to flooding, where you don't have control about how many nodes you reach. So here you can really define how many nodes you want to reach. And another point they have, so this is the fourth point of BubbleStorm, but we will also not go into detail, is to make sure that you always have the specific number of replicas or number of announcements and queries in the network. So to maintain the bubble size. It will not focus on it, so basically we focus on the Bubblecast, how it works, how can we reach 117 nodes. And the idea is to combine somehow the approach of flooding and random walk. So flooding had a benefit, it was quick, so you could reach every node about the shortest path. It was reliable, all of the nodes were reached, but we didn't know how many nodes we reach, so it's growing exponentially. And unbalanced link load, that means that also the nodes contact different number of other nodes. So it's the one node has like 5 contacts and the other one has 1 contact. In the random walk we had the benefit, we have a precise length how long it is. So if we take a splitting factor of 1, then you can really specify with the hop count how many nodes you want to reach. And it is balanced with it, but it's unreliable. One of the nodes might stop and it's done. And we don't reach, we cannot control how long this random walk goes. So it's very, we have a high latency. And Bubblecast tries to combine from the left side, from the flooding, something like a node counter. So you want to control how far your Bubblecast reaches. And it uses a fixed branch factor to cover the unbalanced link load. And it introduces, in comparison to random walk, a branch in every step. So to combine best of the both worlds. How does it work? So let's say you want to reach 17 nodes in this case. So for 117, the slide is too small. But we have an exact number how many nodes we want to reach. So we start with this number, and we decrement it in the beginning. So every node that receives the message, also the initial node, decrements this number because he's also counting as 1. And then he splits the number into what remains. So 17 minus 1, this is the node that we have, and he splits it in 2 equal numbers. And he contacts 2 of his neighbors and sends him the message with the counter of 8 each. And they both also decrement the number and send it on to their neighbors. So they select also 2 of their neighbors, and they send the message out, each with a specifically modified counter, and so on and so on. And you see at the end, by having the counter of how many nodes already received the message, we make sure that in this picture we have really 17 nodes. Yes, so we can, so here we have 8, then we have 6, it's 14, and plus 3, 17. So we have a full control about how many nodes we reach. We can have a full control about how much load is on every node. So every node has just to send out 2 messages and not 5 or 1, or they're not differing. So the load is controlled. The tree depth is also controlled, so it's balanced as much balanced as it's possible. And yeah, we reach just the number of nodes that we want to reach. So if we know what square root of n is, or how many nodes we want to contact, then we can really contact using bubblecast that amount of nodes. And using bubblecast, then it is used to spread the, like I said, the announcements, so the data information. So these buckets are representing nodes, and the green points are the announcements, and the red nodes are the queries. And we have some points where we have some match, and this node can answer for the query and tell, either give me the data or give me the information where the data is. The nice thing is also we can add, so we can make sure that nodes which are more powerful are chosen as neighbor with higher probability. So if you have a very strong node, like this one, which is very active and has many contacts, then he should be more probably chosen as one point in this bubble cast. Because that means that it's more probable that a query or a date, so either a query or an announcement message is going over him, and he can handle it because he's powerful. And weak nodes should have less probability to be chosen in the bubble cast. So we can really define that the node degree should be related to the probability to be chosen in bubble cast, to give stronger nodes the ability to be in more of these bubbles and to have better matches. So it's a small optimization, but it's quite helpful. Okay, so just to summarize on this bubble cast, so it's very nice option to really contact a specific number of nodes. It's used both for the query and data announcements. It uses a fixed branch factor, and this helps to balance the load on the node. So every node has only to send out the same number of further messages. We count the edges, so we count how many nodes are really contacted and not how far the message went. The tree, so we create a tree by this, which is logarithmic depth. So and such a logarithmic tree is fast. So I mean, this is one of the fastest way to spread the message in the logarithmic time scale. And even if we have some message loss, then the effect is not that dramatic. So typically, it's also logarithmic in relation. Okay, and by having really a random topology, we also select random nodes and everything is fine, and mathematically it works out. So I think this is the last slide, yes. So how many nodes do you really have to have? And it is said it is O of square root of n, and if we have the factor c before, so if we have c times square root of n and c is 1, then we have only a success probability of 63%. With 2, it's already 98, and with 4 we have 99.99999% probability. And of course, we could. It's more complicated if you look at it, because also heterogeneity comes into it, and also some loss and inequality in queries and announcing traffic. But roughly to know, it's O of square root of n, and with 3 or 4 as a factor before, we have a very good probability. And even, so just as the last words, even if we take 4 times 2, so both for the queries and the announcements, this O square, the square of n, typically it is still smaller than O of n to reach with full flooding. So it's still very well controllable and more efficient than flooding, but provides the same quality. Okay, this is so far. So we thank you for your attention. We meet each other next week on Thursday, and I wish you a nice weekend and a nice week.